Welcome to lecture 25, where we will learn new tools for calculating derivatives. So these fundamental tools are algebraic theorems. Then we will use derivatives of elementary functions, which we have already partially explored. Then we'll see how to evaluate the derivatives of compound functions, and finally how to calculate the derivatives of inverse functions. Okay, so let's start with the algebraic theorems. Which are 5. First, f plus or minus g, two functions. If we want to take the derivative of the sum or difference of function, this is equal to the sum or difference of f prime plus g prime. Second, if we want to take the derivative of a multiple of a function f, where alpha is just a real number, then this is going to be simply alpha f prime. So notice that theorems 1 and 2 say that the derivative is a linear application. So we will come back on this later, but the thing is that the derivative of the sum of two functions is equal to the sum of the derivative, and instead the derivative of a multiple of the function is the multiple of the derivative. So these two things together say that the derivative is a linear application. 3. The derivative of the product fg prime is equal to f prime g plus f g prime. Then the derivative of the reciprocal 1 over f prime is just equal to minus f prime divided by f squared. And 5, the derivative of the ratio f divided by g, this is equal to a fraction g squared at the denominator, and then we have f prime g minus f g prime. Okay, so we will now prove each of them, and let's start with the proof of theorem 1, namely the fact that f plus or minus g, the derivative of this is equal to f prime plus or minus g prime. Okay, now let's prove the sum, okay, because the difference is totally analogous to this. Now, what is f plus g prime in a specific point x naught? Well, this will be the limit as h goes to 0 of f plus g evaluated at x naught plus h minus f plus g evaluated at x naught, which is just like saying limit h goes to 0. Of course, everything is divided by h, and f plus g at x naught plus h is simply f of x naught plus h plus g of x naught plus h minus f of x naught minus g of x naught. And of course this can be, after a little bit of manipulation, written as limit h goes to 0 of f of x naught plus h minus f of x naught divided by h plus limit h goes to 0 of g of x naught plus h minus g of x naught all divided by h, which finally gives f prime in x naught plus g prime in x naught, exactly as we wanted to prove. Now, of course, this is just using the definition of derivative. We can do the same by just using the differential. Okay, so let's give an alternative proof of this. We need to write f plus g in the point x naught plus h, but this is f of x naught plus we have f prime x naught times h plus little o of h. This is basically f of x naught plus h, and then we have g of x naught, then we have g prime of x naught, and another little o of h. And we recognize now we can rewrite this as follows: f plus g in x naught, which basically takes the first two elements. Then we have f prime of x naught plus g prime of x naught, all this multiplied by h, and this would be the second term. And finally, we simply have little o of h, which proves that this is nothing else than alpha. So alpha, which is the differential, which we know is nothing else than the derivative of f plus h, is equal to f prime of x naught plus g prime of x naught. Okay, which is the end of the proof. Right, so let's now make an intermediate proposition. Okay, before moving to the next theorem, theorem 2, we want to make an intermediate observation or proposition. Okay, which is the following: if f has derivative in x naught, then we can say that f is continuous in x naught. Okay, so this has nothing to do with the algebraic theorem. This is just a general observation that we are making. Okay, we want to prove that if f has derivative in a point x naught, then f, we can conclude that f is continuous at that point. Okay, let's give a proof of this fact, proof of this proposition. We wish to prove that the limit of f of x as x goes to x naught is equal to f of x naught, right? So this is what we would like to have. To this aim, let's rewrite f of x as f of x minus f of x naught plus f of x naught. We can do this just subtracting and adding f of x naught. Now let's evaluate the limit as x goes to x naught of f of x. Well, we need to prove that this is indeed f of x naught. But if we replace f of x with the previous expression, we have this: f of x minus f of x naught plus f of x naught. Okay, and we recognize that in this first two term, we have the numerator of the differential ratio. So next step would be to divide and multiply by x minus x naught. Let's do this. So we have limit x goes to x naught of f of x minus f of x naught divided by x minus x naught multiplied by x minus x naught plus, well, we would have the limit of a constant, but clearly this is simply f of x naught. So in a way we can exclude f of x naught from the limit. And now we see something that when x goes to x naught, this part will tend to f prime of x naught, which we know exists because the function is differentiable. But at the same time we see that this will tend to 0. So clearly this limit is in the end exactly equal to f of x naught. Okay, so this proves the initial statement. If f has a derivative in x naught, then we can conclude that f is continuous in x naught. Okay, so now we are ready to prove theorem 3. Okay, theorem 3 is the one that says the product. Okay, so let's call the product p of x equal to f of x times g of x. Right, so let's take the approach 1, the one that uses just the definition of derivative. So we can say that p prime in x naught is the limit as x goes to x naught of, well, p of x naught plus h minus p of x naught divided by h, right? And because we know that the product is f of x times g of x, this is the limit as h goes to 0 of f of x naught plus h g of x naught plus h minus f of x naught g of x naught. And now this is a common trick that we do whenever we have a product. We need to introduce basically the so-called mixed term. Let me introduce this and we'll comment this after. Okay, limit as h goes to 0. I will rewrite the fraction here, h at the denominator, and the first term is f of x naught plus hg of x naught plus h. Now the idea is I would like to extract the derivative of f, right? So, and the derivative of g. So a mixed term that I can introduce here is minus f of x naught plus h times g of x naught. And of course, because I'm subtracting, then I need to add this again. F of x naught plus h g of x naught. And I'm left with minus f of x naught g of x naught. And now let's make an observation here. What I've done introducing this mixed term, you see that between the first two terms I have this common factor, and if I factor out f of x naught plus h, I'm left with the difference ratio for the function g. Similarly, on the other side, on the other two terms, I have this g x naught in common that can be factored out and will leave me with the difference ratio for f. So let's do this. Let's see what we get. So this becomes now limit h goes to 0 of, we have f of x naught plus h, which is now a common factor, to g of x naught plus h minus g of x naught divided by h. This is one part of it. And then on the other two terms we can factor out g of x naught, which is a constant, so comes out of the limit h goes to 0, and we are left now with the difference ratio f of x naught plus h minus f on x of x naught. And we can now easily recognize that in the first limit this will tend to f of x naught when h goes to 0. This instead will tend to g prime of x naught. This of course will remain a constant g of x naught, and instead this will tend to f prime of x naught. So we can conclude saying that this is f of x naught g prime of x naught plus f prime of x naught g of x naught. Now the same theorem can be proved also with the second approach, the one with the differential. Okay, so let's use the approach 2. Now, because f and g are both differentiable, we can write f of x naught plus h as f of x naught plus f prime x naught times h plus little o of h, and g of x naught plus h as g of x naught plus g prime of x naught times h plus little o of h. And now we proceed with the multiplication, and we try to write p of x naught plus h, which will be just a product of these two expressions, and we immediately see that we have f of x naught times g of x naught, right? Then we have f of x naught times g prime of x naught plus f prime of x naught times g of x naught, all this multiplied by h plus little o of h. And we see that this little o of h is basically the result of 6 terms. One of these terms, for example, is f of x naught times o of h. Another term can be f prime of x naught h times little o of h, and it is easy to recognize that all these 6 terms can be encapsulated in this small of h, and we see now that this is nothing else than p of x naught, and this is simply alpha times h. So you see that alpha now is exactly this expression in square parentheses, and finally we have little o of h. So this finally proves that the differential alpha is f of x naught g prime of x naught plus f prime of x naught g of x naught, as we were looking, and this is consistent with the previous expression. Let's now prove theorem 4. Theorem 4 is the derivative of the reciprocal of a function. Let me call q of x 1 over f of x this function, okay? And we are assuming now that f of x naught is different from 0. This is to say that this function is defined, okay, in x naught. So q of x can be defined in x naught if and only if f of x naught is different from 0. But because f of x is continuous, that implies that this implies that f of x is different from 0 in a neighborhood of x naught. So what I'm saying is that if we have x naught here, and we are saying that in this x naught, f of x naught is different from 0, so let's say f can be something like this. So we have, this is f of x naught, and f of x naught is different from 0. Because the function is continuous, we can find a neighborhood, okay, of x naught, which corresponds basically to this part of the function, right, where the function is different from 0. Okay, so with this in mind, let's see how we can evaluate the derivative, and we will find the we will use the first approach. Okay, so we want to find q prime in x naught, which is the limit as h goes to 0 of q of x naught plus h minus q of x naught divided by h. And this is equal to the limit as h goes to 0 of, well, but just using the definition of q of x, we have 1 over f of x naught plus h minus 1 over f of x naught, all divided by x. And you see why now we need the previous consideration. So this consideration is important because now we can write this. Okay, we can now write 1 over f of x naught plus h, because we know that this is well defined. Okay, so this is now something that we can rewrite as follows. Limit h goes to 0, okay, of 1 over h. If we resolve the numerator, we can write this as f of x naught plus h times f of x naught, and then we have f of x naught minus f of x naught plus h. Okay, this is just a little bit of algebraic manipulation. And now we can write this as we recognize these to be the numerator of, well, these can be these elements. They make up the difference ratio for f with a different sign. We can rewrite this as minus limit as h goes to 0 of f of x naught plus h minus f of x naught divided by h, right? And so this is a first part. Then we have 1 over f of x 0, which is just a constant, so comes out of the limit. And then we have another part of the limit, which is the limit as h goes to 0 of 1 divided by f of x naught plus h. And now we are almost ready, because we see that this clearly is a constant, so this will remain 1 of f of x naught. Okay, this for h that goes to 0, because f is a continuous function, this once again gives rise to another 1 over f of x naught, and instead this thing gives minus f prime of x naught. So in conclusion, what we have is that this limit is simply equal to minus f prime of x naught divided by f of x naught, all raised to the square. Good, so the derivation with the differential approach is totally analogous. So we can move to theorem number 5, which says that f divided by g, if we want to take the derivative of this is equal to g squared at the denominator, and then we have f prime g minus f g prime. Now, why is that? Well, this is quite simple to prove, because we can think of f divided by g prime to be simply the product of f and 1 over g. And if we now apply the theorem on the product, we have that this is f prime times 1 over g plus f times 1 over g prime. And we can now apply the theorem on the reciprocal of a function. So this becomes f prime 1 over g, and then we have minus f, this is g prime divided by g to the square, which if we make in a single fraction, we get g squared, and then we have f prime g minus f g prime, which is exactly what we wanted to prove. Now, there is an important theorem which we will state, but we will not prove because we don't have the tool yet. This will be proved much later in the course, and this theorem is about compound function. So we want to take the derivative of a compound function. For example, if we have f of g of x, okay, so we are using two functions, f of x and g of x, and we are using g of x as the argument of f. So this gives rise to a compound function, and the theorem says that if we want to take the derivative of this compound function, this is equal to f prime evaluated at g of x times g prime of x. Okay, we will be using this theorem without giving a proof now. Okay, we will prove it later. And there is another theorem which refers to the inverse function, and also this theorem is not gonna be proved here, but we need to use this theorem. So we will state the theorem, and the theorem goes like this. So we have, let's suppose that delta is a positive number and r is another positive number, and we have a function f, okay, that is defined in a neighborhood of x naught, or which is wide, has a width of delta. So f goes from x naught minus delta to x naught plus delta. So this is where the function is defined, and the image will be y0 minus r, y0 plus r. So this is the function f, and we said that this function is invertible. Okay, let me copy this here. This function is invertible. Then we have another function g. So let me make a graph here. Maybe this will help understand. So let's say that we have this function here. This is the function f. Okay. So this is x naught, and we are saying that we have x naught minus delta, x naught plus delta. So this is the interval where the function is defined, and this of course will identify on the graph of the function this part of the graph, and we are saying that x naught has an image f which is y naught, okay, and the interval x naught minus delta, x naught plus delta will correspond through f to an interval y naught minus r, y naught plus r. And we are saying that within this interval, okay, the function is invertible. So we can define then a new function g that goes from y naught minus r, y naught plus r into x naught minus delta, x naught plus delta, okay? And of course we are assuming that f of x naught is equal to y naught, okay? If we are in this condition, then we can say that if f prime of x naught exists, so in the assumption that f has derivative in x naught and this derivative is f prime of x naught, then we can say that the derivative of g in the point y naught is equal to the inverse of the derivative f prime evaluated in x naught. And if we want to re-express this in terms of y naught, this can be done as follows: 1 divided by f prime. Remember that x naught is nothing else than g of y naught because of the invertibility. Yes, so this is the theorem. Now, what we will give now is a draft of proof, okay? This is just a draft of the proof. The real proof will be given much later in the course, but one way of proving this, again, this is not totally correct, but one way of thinking of this is this: if we know that f of g of x, okay, because these functions are one the inverse of the other, well, in this case this is just equal to x. Now if we take the derivative of the left hand side by using the compound function theorem, we have that this is f prime of g of x, okay? Let's say that we want to do this in a specific point x naught, okay? So we can say this g prime of x naught equal to 1, because if we take the derivative in a specific point, so let's say that we leave x here, and then we want to evaluate the specific derivative of the left hand side in a specific point x naught. So this is what we get. But from this, clearly we have that g prime evaluated at x naught is equal to 1 divided by f prime of g x naught. Okay, so this is clearly exactly the same of the theorem that we have just stated, right? So if you look at this expression, this is exactly the same as this expression. So we just proved that the inverse, the derivative of the inverse function is given by 1 over f prime of g of x naught. What's wrong with this is that we did not prove, we have assumed without proof, without proving it, that g of x has derivative. So this is the missing part of this proof. This is why this is not a complete proof. We said that f is a function that has derivative. If you look back at the hypothesis of our theorem, we said that we are assuming that f prime of x naught exists, okay? But then no one said that g has derivative. Okay, so we couldn't just assume this. We need to prove this. To prove this theorem, we need other tools. But for the time being, we'll just refer to this theorem. We will assume that this is correct. Okay, and we will be just using this. Now it's time to apply all these ideas to some elementary functions. Okay, so let's start with the example 1. We know that we proved in the previous lecture that if we have f of x equal to e to the x, the exponential, right? We know that f prime of x is just equal to e to the x. Now, what we would like to do is find the inverse, the derivative of the inverse. And we know that the inverse of f of x is g of x equal to the logarithm of x. All right? So, what will be the g prime of x? Well, by just applying the theorem of the derivative of the inverse, we know that this is equal to 1 divided by f prime evaluated at g of x, right? So this is equal to 1 divided by, well, what is the derivative of f is e, but e to the x, but this needs to be evaluated at g of x, which is e to the logarithm of x. Finally, we get 1 over x, okay? So it's very easy once that we assume that the theorem is valid. Let's now consider the inverse. Let's take the function f of x tangent of x, and we know that, well, let's evaluate the f prime of x. Okay, now f prime of x means if we replace the expression for the tangent, we have sine of x divided by cosine of x, derivative of this, right? So we have the derivative of a quotient, and we know how to deal with this now because we have a theorem. So we have cosine square of x, then we have the derivative of the sine, which is cosine times the denominator is cosine square of x minus sine square of x. And of course this is something that this is a plus. So we have two possible ways of representing this. We can rewrite this as 1 divided by cosine square of x, okay? But there is also an alternative way of representing this. An alternative way is just using the fact that we can split the previous fraction, okay? We can split this fraction into two parts. We can write this as cosine square of x divided by cosine square of x plus sine square of x divided by cosine square of x, which is just 1 plus tangent square of x. Okay, so in conclusion, let me rewrite this conclusion here. F prime of x can be written in two ways, or 1 divided by cosine square of x, or 1 plus tangent square of x. Okay, we can do this. Right, now, for the inverse function, let me consider g of x. We know that the inverse is arctangent of x. What will be g prime of x? Well, g prime of x, by using the theorem, is 1 divided by, right, the f prime of g of x. Let me use this space, or I can leave it here, yes. And if we use now this form of the derivative of the tangent, we can rewrite this as follows, as 1 divided by f prime is just 1 plus tangent square of x. We need to replace x with the inverse, which is the arctangent of x. And this is now simply 1 divided by 1 plus x squared. Good. Example 3. Let's consider the function f of x equal to the sine of x, and we know that f prime of x is the cosine of x. Okay, Now, we would like to find the derivative of the inverse g of x arc sine of x. Okay? Now, the g prime of x is 1 divided by what? Well, again, we need to apply the theorem f prime of g of x, which in this case is 1 divided by, what is f prime is just the cosine of g of x, but the g of x is the arc sine of x. Now, we have a little bit of a problem here because we need to find the cosine of the arc sine, so they do not cancel each other. What we need to do is basically to re-express the cosine in terms of the sine. So we can rewrite g prime of x as 1 divided by, remember that the arc sine of x, let me remind you where we are here. Okay, so if this is the unit circle, the arc sine of x is defined between minus pi over 2 and pi over 2, right? So the arc sine of x, when we inverted the function, we had to limit basically the definition of the function for the function to be invertible. Okay, so the arc sine of x is defined between minus pi over 2 and plus pi over 2, and we see that in this interval, okay, the cosine is always positive. So what we can do, we can rewrite this as the positive square root of 1 minus sine square of the arc sine of x. And now this is easy because this is becoming just 1 divided by 1 square root of 1 minus x to the square. So this is the inverse, this is the derivative of the inverse function. Now, in a similar way, we can compute the inverse of the cosine. So let me go to the example 4. We consider now f of x as the cosine of x, and we know that f prime of x is equal to minus sine of x. Now we would like to find the inverse, the derivative of g of x, which is the arc cosine of x. Okay, let's apply the theorem as always. So we have that g prime of x is equal to 1 divided by f prime of g of x, and this f prime of course is minus sine of x, so we have minus 1 divided by sine of g of x, which is the arc cosine of x. And we have another, again, the same problem, because the sine and arc cosine, they do not cancel each other. We need to express sine in terms of the cosine. And if we once again reconsider the way we define the inverse of the cosine, remember that we define the inverse of the cosine between 0 and pi. In other words, the arc cosine of x is a function between 0 and pi, and we see that in this interval the sign is always positive. So we can re-express this as 1 divided by simply the we have a minus in front, okay, because we have that minus in front that comes from the derivative of the cosine. So we have minus 1 divided by the positive square root of 1 minus the cosine square of arc cosine of x. And this is now simply equal to minus 1 divided by square root of 1 minus x to the square. Now we can conclude this lecture with a summary of derivatives of elementary function. The one that we can evaluate at this point. So let me start with the first one, is the derivative of a constant. What is the derivative of the constant? Well, this can be easily proved to be zero. Just think about what a constant is in terms of a graph, okay? It will be just a horizontal line and the slope is zero, whatever point you pick. Then we have the x to the n, the power, okay, with an integer exponent. What will be the derivative of this? This is simply n times x to the n minus 1. We can give different proofs for this. I will just give a proof based on the induction, okay? So this is good also to review the ideas of induction. So we need to remember that in the induction, when making a proof by induction, we need a base case and an induction step. Okay, so this is the base step. Base step for n equal 1, okay, we see that we have x to the 1 derivative, which is basically the derivative of x, but the derivative of x is equal to 1, which is exactly what we get if we replace n with 1. So we have 1 times x to the 1 minus 1, which is 1 x to the 0. So this is 1. Okay, so this is done. Okay, let's go to the induction step. What is the induction step? Well, we assume that xn derivative is equal to n times x to the n minus 1, and we want to prove that x to the n plus 1 derivative is equal to n plus 1 x to the n. Okay, so let me start by writing x to the n plus 1 derivative. Okay, I can write this as x times x to the n derivative, and now applying the algebraic theorem of the product, we see that this is equal to x prime times x to the n plus x times x to the n prime. But x prime is simply x, so we have simply x to the n here, and then we have x. Now, applying the hypothesis of the induction step, we see that this is n times x to the n minus 1, which now becomes x to the n plus n times x to the n, which is nothing else than n plus 1 x to the n. And this proves the second part of the induction proof, right? Okay, so third function, which we already prove, is that the derivative of the exponential is simply equal to e to the x. Okay, and now we can use this also to find the derivative of a to the x prime, okay, where a is any positive number. Okay, so we have another exponential with a new base. Okay, the base is now a positive number, and we want to find the derivative of a to the x. And it turns out that this derivative is given by a to the x times the logarithm of a. And we'll prove this now. Proof. Now, what we can do is basically we have to find the derivative a to the x. Okay? We can rewrite a to the x as follows. E to the logarithm of a to the x. Yeah, this is pretty much the same. And by using the properties of the logarithm, this becomes e to the x times the logarithm of a, all this prime. And now we have the result 3. So we are now applying the theorem on the compound function. We know that this is going to be e to the x logarithm of a times the logarithm of the exponent, the derivative of the exponent, which is simply logarithm of a. So we can rewrite the first by considering that this is simply e to the logarithm of a all raised to the x times logarithm of a. This is a to the x logarithm of a, which will conclude the proof. Okay. Another interesting result is the following. 5. X to the a. We need to find the derivative of x to the a, and this is basically a power. However, the variable now in the base is not in the exponent. Okay, and this turns out to be a times x to the a minus 1. Okay, let's prove this. And all the proof of this type are always using the same tool, which is basically the transformation to the exponential. In fact, we can rewrite x to the a prime as the derivative of e to the logarithm of x to the a, which is again the derivative of, by using the properties of the logarithm, e raised to the a logarithm of x. And once again, using the compound function derivative theorem, we know that this is e to the a logarithm of x times the derivative of the exponent, which is simply a divided by x, because the derivative of the logarithm of x is 1 over x. So this is e to the logarithm of x all raised to the a times a over x, which is simply x to the a divided by x, which again is x to the a minus 1 times a. Okay, which concludes the proof. Okay, so this concludes the summary. Together with the other derivatives that we have already evaluated, this is all that we need for our course in terms of derivative of elementary functions. And of course, by using now all the theorems, the algebraic theorems, compound function, inverse function, we can find also derivatives of other functions that are just obtained by putting together these elementary functions. Let me give you an example of this. Let's suppose that we need to evaluate the derivative of the cosine of logarithm of x. Okay? And of course, this is only valid for x larger than 0, where the logarithm is defined, right? So we can use the compound function theorem here. And we see that because the derivative of the cosine is minus sine, we have minus sine evaluated at the logarithm of x. This is the first part. And then we need to multiply by the derivative of the argument, which is the derivative of a logarithm of x, which is simply 1 over x, right? So this is an example. Second example, let's say that we want to evaluate the cosine of x times the logarithm of x. Okay, we want to evaluate the derivative of this product. Then we can use the algebraic theorem related to the product of two functions. So we have the derivative, the cosine, which is minus sine of x times the logarithm of x plus cosine of x divided by x. Oh, this was a straightforward application of that theorem. Then let's suppose we want to take the derivative of x raised to the x. As always, when we have powers with the functions in the base or in the exponent, we need to use the transformation to the exponential. So this becomes e to the logarithm of x raised to the x prime. And this is again e to the x logarithm of x, all in derivative, right? And this is equal to, of course, e to the x logarithm of x times the derivative of the exponent, which is now a product. So we have simply logarithm of x plus 1, because we have x times 1 over x. Okay, so we can rewrite this in this form, simply x to the x times 1 plus logarithm of x. A final example now, more in general. Okay, let's suppose we have an f of x raised to the g of x. All this, we need to take the derivative of this, right? And transformation to the exponential, this becomes e to the g of x that multiplies the logarithm of f of x. Okay, we need to take the derivative of this. And this now becomes simply f of x raised to the g of x times, we need to take the derivative of the exponent, which is now a product. Well, it is a compound function actually. So we have g prime of x times the logarithm of f of x plus g of x. Then we have 1 over f of x, and then we need to multiply by f prime of x.